Everyone. Okay, we talked about making a little video for rules of limits. Here it is. Hopefully, it's like 10-ish minutes. But let's go. Rules of limits or rules for limits. Let little a and cap B be real numbers, and let f and g be functions such that the limit as x approaches a of f of x equals cap a, and the limit as x approaches little a of g of x equals b. So this just says basically you have two different functions. Like let's say it's on the same. Here's A, um, maybe F is A and B is pink. Okay. So then here's the limit for G, and here's the limit for A. Whoops, yeah, no, that's the right color. So then basically this is A, whoops, and this is B. Okay, so that's what that says. Um, just for these are all algebraically, okay, for one through everything, actually. 1 through 5. This is just for solving algebraically. So if k is a constant, then the limit as x approaches a of k equals k. So what that means is if I'm just a number, like say y equals 2, all right, so if that's just 2, then the limit is k. No matter where we are on the horizontal, the limit is k because, right, the line is just k all the time. So of course, the limit's going to be k. The constant times function rule says if k is a constant, then the limit as x approaches a of k of f of x is equal to k times the limit of f of x as x approaches a, equaling k times a. So if I come over here and say if I have the limit as x approaches, I don't know, 3 of 2 times, I don't know, 3x minus 9, then I can say this is 2 times the limit. Oh, I already made that. Let me change plus 9. That's a plus now. The limit as x approaches 3 of 3x plus 9. Okay. Well, essentially what that says is I can solve just the limit and ignore the 2. Say that this is 2. Now, to drop the limit, we have 3. Oh, sorry, hang on. I just realized that parenthesis needs to be on the outside. Whoopsies. Need my rainbow pen back. There we go. 3x. There we go. So this is 3 times 3 plus 9. So it's 2 times, well, 3 times 3 is 9. So 9 plus 9 is 18. So then it's now just 2 times 18, which is what, 36? That's all that means. Sometimes, a lot of times, you'll find out just pulling out that constant makes our lives easier. 3. So we can split limits into separate functions. So if I have, I don't know. Well, even if I can say the limit as x approaches 3 of, even if it's 3x plus 9, we wouldn't necessarily do this for this exact example, but this is the concept. We can split them up into their own limit. And there are various reasons why this makes things easier. So here we can say, like, okay, we can throw in the 3, and then the next one we know is 9 from rule 1. And again, we just get 18. Oh, no, sorry, not, 18. So again, we can split the limit into its own separate limits. If the function is plus or minus stuff, we can put them in their own limit. 4, same thing with multiplication and division. Okay, 4 and 5, same thing's true. We can split them up into their own limits as needed. Okay, so let's say again, I have, I don't know, the limit as x approaches 3, or let's go with a different number. I don't know, 1 of 3x minus 9 times 2x squared plus 1. Well, we can split this up into their own limit. Usually we would use this rule if popping in the little a, the 1, causes problems. It's not really happening in this instance, but just showing you how it's practiced or how it's, sorry, I can't do multiple things at once, just showing you how it's put into action. Okay, so then we could just take the limits independently. So it's 3 times 1 minus 9. And then let's see, 2 times 1 squared plus 1. So let's see, 3 times 1 is 3 minus 9 is -6. 2 times 1 squared is 2 plus 1 is 3. So then we end up with what? -18. Again, this is not the example of when we would use this necessarily, but just to show you what the rule is in action. So then, same thing with division. So say I have the limit as 1 was kind of nice to work with. Say it's 3x minus 9 over 2x squared plus 1. Same thing. We can take the limits independently of each other. Okay. So this is really nice for cases where throwing in and this, like our 1 is an arduous task, or maybe we need to find some like loophole algebra to manipulate and get things to work for us. But essentially, this is what we're allowed to do. So then we know this is what, -6 over 3. So that would be -2. Where am I? Okay. And of course, yes, we can never divide by 0. That never goes away. So polynomial rules. If for a polynomial, if p of x is a polynomial, then we just find the limit by slapping in the value, right? That's because polynomials, right, we talked about with continuity, they are continuous everywhere. So if this is a, then of course its limit value is p of a because we're continuous everywhere. Power rules, basically, same thing we're used to with exponents. Okay, if there's an exponent, we can take it out. So if there's an exponent to the function, we can basically find the limit and then raise it to an exponent. So like if I have the limit as x approaches 1 of, say, I don't know, let's just keep on with 3x minus 9 squared. Okay, well then this could be the limit as x approaches 1 of 3x minus 9 quantity squared. Is that the case? Let me make sure. Always good to verify anything you think. That's the limit. Oops. Actually, I can just toss that sucker in. So 3 times 1 minus 9 is equal to -6. So then if I were to square, that would be a square. Doop, doop. One more. Boop, boop. Where are you, rainbow pen? Squared. That's 36. Let's double check. The limit as x approaches 1. Well, 3x squared, oh, excuse me, not the squared there. The squared there is the limit as x approaches 1. Now I'm going to distribute, aka FOIL that out. That is what? 9x squared, combine and double. That's -27 times 2 is what? 54? -54. Making myself do mental math. I hate that. Okay, so then if we toss in the 1, 9 times 1 squared minus 54 times 1 plus 81. 9 minus 54. I hate mental math. Okay, let's just not do it. Whoopsies. 9 minus 54 plus 81. 9 minus 54 plus 81 is 36. Yeah, okay, great. I'm so smart. Yay, go us. Verifying our solutions. Always verify when you're not sure. Don't always just assume something that should happen does happen, because that's how math will get you. Okay, so just to note, sorry, I know I'm talking fast because I'm trying to go fast because I just hope you watch this. And I know if you see a long timeline, you'll be like, ugh, I'm not doing it. But please. Okay, exponential rules, same thing for exponents. Logarithm rules, same thing. Basically, you can take the log in and out. Whoopsies, I thought I was a highlighter. Sorry. There we go. So again, you can move the log in and out, up, it's me, yeah, up and down the exponential, and you can take the log. It's very nice. We'll kind of talk about this more as needed, but we don't really go into it in this class a whole lot, to be honest, 8 and 9. And then equality rule for limits. So the limit as x approaches a of f of x equals the limit as x approaches a of g of x if f of x equals g of x for all x equaling a. Basically, if these two limits are the same, if these limits are the same, then those graphs are likely the same. Okay. Well, not likely, they are the same. And we'll kind of pop back to some of these as we go along for what we may need. But we'll kind of talk about them also in terms of like how they're nice to us for derivatives and integrals later on. But that's it. So hopefully this helped to understand the rules. We'll circle back to them and I'll try to refresh your memory for those as well. Okay. Bye. Let's see if I can stop the recording. Okay, yes.